Welcome to the series on linear algebra. In the coming videos, we are going to learn about topics like vectors, matrices, their linear combinations, how to use them to solve systems of linear equations, and a lot more. But keep in mind that we won't be diving too deep into the intuitions about what vectors are and what on them actually mean. As in this series, we'll primarily be focused on understanding the concepts and understanding on how to use them to solve problems, as it's more oriented towards preparing for exams. But it's always a good idea to understand these beautiful topics in detail and get the actual intuition behind them, and there are a lot of good sources available for that. For example, this linear algebra series by 3 Blue 1 Brown, or textbooks on this topic by Gilbert Strang, and many more. In this series particularly, we are going to try to keep our pace a little fast so that we can quickly understand the concepts and see how you can use those concepts and apply them to real world problems. So let's get started. First of all, let us understand what vectors are. So a vector can be thought of any long list of numbers. There are a lot of multiple ways to look at vectors, but for the simplest part, any list of numbers can be thought of as a vector. For students from a more physics background, a vector is mostly represented as an arrow pointing in a certain direction, which has some magnitude, which is shown as the length of that arrow and a direction associated with it, which is a great tool to visualize these vectors and the operations happening on them. But they are only limited to 2 or maximum 3-dimensional vectors, because it's really hard to visualize arrows in more than 3 dimensions. But it will be a good starting point to actually understanding what these vectors are. So we'll also be using the analogy of a vector as an arrow with some magnitude pointing in some direction. But just to keep in mind, vectors can be of any length. And the perspective of looking at vectors as a list of numbers is especially useful if you're a computer science student, as that corresponds directly with arrays. So manipulating arrays you can think of as working with vectors. So with that in mind, let's start with a vector. Let's take A as a vector. So let's say we have a vector with the values 1 and 2. How would you represent this on our two-dimensional plane? So this is a vector that is sitting at the origin and pointing towards the point which has the x-coordinate as 1 and the y-coordinate as 2. So this vector right over here can be represented in this notation 1 and 2. So let's take another vector, let's say B, and let's say this is 3, 1, 3, 1. So where would this how would you represent this vector on this 2D plane? Again, the x coordinate for this would be 1, 2, 3 over here, and the y coordinate is just 1. So this is the vector B. This was the vector A. So this is how you can visualize vectors on a 2D plane. And in a lot of places, you can also find these vectors written in a special notation, something like A equals to 1x hat plus 2y hat. So now this is exactly the same thing as this and this. This is just one more type of notation to represent this vector. Now to understand what we are saying over here, we have to understand what this x hat and y hat are. So the x hat is nothing but a vector, let's take another color, that is just one unit long in the x direction. And the y hat is, again, let's take a different color, is just another vector that is 1 unit long in the y direction. So you can say that we can form this vector A by taking one of these x hat vectors and 2 of these y hat vectors. So over here, there is one more concept that we haven't seen yet and that is the addition of two vectors. So now we are defining this vector A as the addition of two type of basic vectors that we defined arbitrarily. So in a plane, when you define some vectors arbitrarily like this, they are called the basis vectors of that plane. I could have represented this vector A using any other choice of basis vectors. I could have taken my x hat to be an vector with the magnitude of 1 pointing in the minus x direction, and in that case I would have had to add a minus sign over here, but that would still represent this vector because the choice of the basis vectors is arbitrary. It could be anything, but it's just a way that you can represent a vector of your choice as the linear combination of the basis vectors. So we are actually jumping a bit ahead of ourselves since we haven't seen what addition of vectors mean, what the linear combination of that means. But I just wanted to show you first that there are multiple ways to represent a vector. So in the most abstract way, a vector is just a concept in mathematics that follows some axioms. So those axioms are listed over here. We'll go in deep into them in some other video, but for now, let's go ahead. So now to understand all this better, first let's erase this. Let's understand what are some operations we can perform on these vectors. So first of all, as you can see, a vector is just a list of numbers, right? So let's say we have this vector A itself, and what can you do with A? So in this plane, as we see, we can represent a vector by an arrow over here. One possible operation we can do with this is scale this vector, right? This arrow, you can take this arrow and you can scale it twice as long. You can make it thrice as long. So how do you represent that? So that is nothing but multiplying a vector with a scalar value. So if we have a vector 1, 2 and we can multiply that with a scalar value of 3. So as we just saw, that represents that we take this vector and scale its magnitude by 3. So if we did that to A in our example over here, where would that take us? So now what is this point on the plane? And just a little bit of a correction. This over here was the x hat and this is the y hat. Yeah, so as we can see, this would take us at the point 3 in the x direction, and this would be the point 6. So scaling the vector A, which is 1, 2 by 3, we got a vector that starts at the origin and points toward the point 3, 6. So this got us to a vector that points at 3, 6. So scaling a vector is nothing but just increasing its magnitude by some factor. We do not rotate the vector, we do not shift the vector, we just change its magnitude. And to do this mathematically, what you do is you just multiply this value, the scalar value, with all the elements of the vector. So to multiply 3 with this vector 1, 2, we just multiply with the 3 with 1 and we also multiply it with 2. So we get 3 and 6. So now let's just similarly do that with B. So now if I say that I want to multiply the vector B with a scalar 7, you know how we do that. We can just multiply each of its elements with the scalar. So 7 multiplied by 3 would get us 21 and 7 multiplied by 1 would just get us 7. So this would be a vector which will be pointing to a point whose x coordinate is 21 and the y coordinate is 7. So it would be some really long vectors in this direction. So let's just remove that for now. But you get the idea of scalar multiplication with a vector. So now to come back to this type of notation, this way of representing a vector in terms of basis vectors, we also have to learn about the addition and subtraction operations between the vectors. How do you add two vectors? So for that, in the terms of, again, going back to our analogy of vectors being arrows on a plane, let's say you had this vector pointing over here and another vector like this pointing over here. To add these two vectors, what we actually do is, so let's actually just define the value. So this is at minus 1, 1, and this one is also at 1, 1. So now to add these vectors, what we do is we just take one vector and move the tail of that vector to the tip of the vector that we are trying to add it to. So if we want to say that our vector over here, the vector A, the blue vector A, was minus 1, 1, and the vector B, the red one over here, was 1, 1. To add these two together, what we do is we just move this vector B to the tip of the vector A. And our new vector is the vector that starts at the tail of the vector A and goes towards the tip of the vector B. So this green vector over here is the addition of A and B. Let's just call this C, and the coordinates for C are 0, 1. So now you might have guessed how the addition and subtraction works in terms of vectors, but let's just look at that formally. So in this case, we added the vector A, which was minus 1, 1, plus we added it with the vector B, let's use the same colors, which was 1, 1, and we got the green vector C, whose coordinates are, as we can see from this graph, 0, 1. So looking at this equation, you can tell that when we add or subtract two vectors, what we do is we add or subtract the corresponding elements. So to get this element of our resultant vector, we just take this element plus this element. To get this element of our resultant vector, we just take this element plus this element. So this could have been done even if the vectors were not just two-dimensional. So for example, if we have two vectors like this, minus 1, 7, 21, 3, and let's say we subtract another vector, and that is 1, 3, 4, 5. So the resultant vector would be just this element minus this element, so it would give you minus 2, this element minus this element, 4, this element minus this element, 17, and this element minus this element, minus 2. So it's not very difficult to add or subtract two vectors or multiply them with scalars. You just do all the operations with the corresponding elements. When you multiply it with a scalar, the scalar gets multiplied to all the elements of the vector, and when we add or subtract the vector, we add or subtract the corresponding elements. And the same is also true with matrices, but we'll get to matrices in the next video. So now let's quickly recap what we learned in this video. So we learned what a vector is. So a vector is just a mathematical concept that follows some axioms, but for the sake of our series, we are assuming the vector to be a long list of numbers, and if the length of that vector is 2, we are mostly going to represent that using an arrow in a 2D plane. And we also learned how to multiply a vector with a scalar and how to add multiple vectors together. And using that, we also learned how to represent vectors as a linear combination of basis vectors. So a linear combination is nothing but just multiple vectors which are scaled and added with each other. So this over here, this equation right over here, -1 times x cap minus 2 times y hat is just a linear combination of these two vectors. So we also learned how to compute these linear combinations and how to represent our vectors using these linear combinations. So now let's get to some practice. So let's compute this linear combination. So first of all, what we do is we'll multiply these scalars inside of these vectors. So this vector would become -2, 4, and 20, plus this vector would become 48 minus 96 and minus 36. And then we just add the corresponding elements together. So this would be 46, 92, minus 92, and minus 16. So as you just saw, it's super easy to calculate linear combinations of these vectors. And we'll see that how all these operations that we are learning, even though they seem pretty simple, will help us solve a lot of problems. For example, solving a system of linear equations in some unknown variables. To finish off, let's take one more example. So how would you solve this linear combination of vectors? So first, again, take the scalar, multiply that into the vector. So over here, we'll have 27 times 3, which would be 81, 6, 12, and minus 18, minus, we do this again, so we have minus 21, so this, then we have 7 3s are 21, 14, 7 into minus 1 minus 7, and again minus 7, then plus, we have 0, minus 36, 28, and 12. Then again we just add the corresponding elements. So we have 81 minus 21 plus 0, so 60, 6 minus 14 plus minus 36. So minus 14 and minus 36. So 6 minus 14 gives us minus 8, and minus 8 minus 36 gives you minus 44. Then we have 12 minus minus 7, so plus 7, so we have 19. 19 plus 28 is 47, and minus 8 minus minus 7, so that gives us minus 11, and plus 12, so we have 1. So this is the answer. So in the next video, we'll learn more about matrices and how to represent linear equations as vectors and also how to solve them. If you like this video, don't forget to subscribe if you're also preparing for exams like GATE 2026, and thanks for watching.